Okay, so we're exploring the ideal gas law, right? Pressure times volume is proportional to temperature, and there's some constant there. We haven't looked at that in any detail. And so it's true that pressure times volume over temperature is this constant. And so, right, let's say we have a gas, an ideal gas, with some pressure Pi, some initial pressure Pi, and the volume, the initial volume is Vi, and we divide that by the initial temperature, Ti. That has to equal to the final pressure times the final volume divided by the final temperature, because both of these things are equal to C. So let's say that we have an initial pressure. We have an ideal gas with an initial pressure Pi, an initial volume Vi, and an initial temperature Ti, and we don't change the volume. So V final is also equal to V initial, but let's say that T final is twice T initial. So we can ask, what does that imply for P final? Okay, so P final, right, related by these relations, P final is equal to P initial over T initial times T final, right? We're bringing it to that side, so we multiply times T final, and these quantities are given. So we have 2P initial times T initial. So this is P initial. I just brought the 2 to this side, so I did 2T initial. So we had 2P initial, T initial over T initial, and that is these cancel out, so that's twice P initial. So the pressure, unsurprisingly, doubles for this ideal gas. But let's consider the implications of this. We know that the concept of work, right, we define that as the integral of the force over some distance. And if we consider, so we're considering the part of the force along the displacement, if you will. So let's get rid of the dot product, but let's use the relationship between force and pressure. Right? Pressure is force per unit area. So for this gas, we have some force per unit area. And if that's the right way to think about this, and we'll see that it is, we have force is equal to pressure times area. So we are integrating a PA thing over some distance at a constant, at a value of P that doubles goes from Pi to 2Pi, but this Pi to 2Pi, this is, right, so this little piece here is a little volume, area times the tiny distance, that's pressure times a little volume dV. But this is 0 because there is no change in the volume. So we know that PV, so we can say, but PV is an energy. Okay, so we have an energy in this system, and P final V final is equal to twice P initial V initial. All right, so the energy doubled. So energy doubled, but without work, because we just showed that if we can think of force and pressure, if there's a notion of pressure for this gas that relates to a force in this way, that seems straightforward. Then we have absence of work. And so, right, the work in this case is P dV. And so for the ideal gas, when we think of work, we're integrating this kind of a thing. And so this is the kind of thing that we're thinking about for a gas. And here we are in a situation where P and V, we have to integrate this kind of a quantity. But there must be some difference in volume. And in this case, we're going from some value here to some other value over there. Or we're doubling the pressure. It's not quite double, but we're doing it at a constant value. So when we integrate this, we get 0. So if no work is done, right, and where is this energy coming from? And so we know about the concept of work applied to, point particles or little balls or billiard balls or blocks. But there was also another way of getting energy for little balls or point particles or blocks, and that was through collisions. Right, so we saw that if we have a block of mass m just sitting on some surface, and then we have another block, say, of mass m or some different mass, and it comes in with some speed v naught, they collide together. They could be moving at different speeds afterwards, but clearly this one is not going to be just sitting there. It'll be moving with some speed, and therefore it'll have some energy, so it acquires some energy through collisions. And that suggests that that's the kind of thing we need to appeal to in order to find the source of this new energy. Okay, so it's going to be collisions, and that's not work. That's going to be what we call heat. Okay, so collisions and heat, and here we have work and differences in volume, and it's these kinds of things together that will ultimately allow us to sort of generalize the energy concept into the first law of thermodynamics. But the important thing to notice here is that we're starting to get a notion that we're going to need to think about this gas as a collection of little objects of different masses or of the same mass. If it's all the same material, we put it into some volume, and temperature somehow is going to have to emerge from this. From these considerations, there's no immediate conclusion about the size of these objects. We won't know how big they are. We'll have to see further considerations that allow us to think about their size, and ultimately this will lead us to what's called kinetic theory.